Have you ever considered how Keel conductance influences depolarization? Intriguing, isn't it? Let's delve into this fascinating interplay. Keel conductance refers to the ease with which chloride ions traverse the cell membrane. It's a bit like a gatekeeper, controlling the flow of these ions in and out of the cell. Now let's bring depolarization into the mix. Depolarization is the shift in a cell's usual negative membrane potential towards zero. It's like a party invitation, coaxing the usually reserved ions out of their comfort zone. So how do these two concepts dance together? Keel conductance influences the rhythm and magnitude of depolarization. If Keel conductance increases, the chloride ions flow more freely, slowing down the rate of depolarization and reducing its extent. Conversely, if Keel conductance decreases, depolarization can occur more rapidly and to a greater degree. So, in essence, Keel conductance plays a vital role in controlling the speed and degree of depolarization. Now that we've established the connection between Keel conductance and depolarization, let's delve further into how Keel conductance sets the cell's spiking threshold. Picture the spiking threshold as a tipping point. When the cell's internal conditions reach this point, it triggers an action potential, essentially firing an electrical signal. Keel conductance can influence where this tipping point lies. Imagine a seesaw. On one end, we have an increase in Keel conductance which raises the spiking threshold, making the cell less likely to fire. Conversely, on the other end, a decrease in Keel conductance lowers the threshold, making the cell more likely to fire. This balance is crucial in regulating the cell's activity. But why is this important? Well, it's because the spiking threshold is not a fixed value. It's dynamic and can be influenced by various factors, including Keel conductance. This means that Keel conductance acts as a sort of gatekeeper, determining when a cell will fire an action potential. So what would happen if a neurotransmitter such as GABA opened Keel channels at the postsynaptic membrane? Let's find out. Neurotransmitters are the chemical messengers of our nervous system. They are able to modulate the activity of neurons, and one of the ways they do this is by opening chloride channels on the postsynaptic membrane. When a neurotransmitter like GABA binds to its receptor, it triggers the opening of these channels. This allows chloride ions to flood into the cell. As these ions are negatively charged, their influx increases the negative charge inside the cell. This change in charge makes the inside of the neuron more negative relative to the outside, a state known as hyperpolarization. Hyperpolarization moves the neuron further away from the threshold needed to fire an action potential, effectively inhibiting the neuron from firing. This is a key mechanism of neuronal inhibition, helping to balance the excitatory signals in our nervous system. In this way, neurotransmitters can regulate neuronal activity by modulating Keel conductance, and in turn, influencing depolarization.